We're going to take a look at the mean value theorem. The mean value theorem is one of three existence theorems that we have. We've already talked about, I think, two of them. One of them was the intermediate value theorem, which said if you have a continuous function on the closed interval from a to b and the function y equals f of x, then the function passes through every point between f of a and f of b. It has to go through all those intermediate points. We also had the extreme value theorem that said if you have a continuous function that on a closed interval from a to b, that function will have a maximum and it will have a minimum on that closed interval. The last one is the mean value theorem. Now, consider each the continuous differentiable functions, and that should be functions, not function. On the closed interval from a to b shown below. At how many points will the slope of a tangent line be parallel to the slope of the secant line shown? And the secant line I've shown is dotted. So how many places on this one will we have a tangent line that's parallel to this dotted line? So if I was drawing in a tangent line, how many of them would be parallel to the dotted line? Yeah, that's exactly right. There'd be two. And I think for a lot of people, the easiest way to see this is to, no kidding, physically I can't do it because it's stuck to the screen, but take your piece of paper and turn it until the dotted line is horizontal. Now try to ignore the paper and draw horizontal lines, and I totally missed. There'll be one right about here and one right about there. I can do better than that. Try to ignore the paper. Only look at the graph. Do you need a ruler?
I think my depth perception.
Don't you play baseball?
Yeah. I don't know why, I just can't see it as being a straight line.
Oh, it's not bad. Yeah, it's not like you drew something horrible. So in this case, there were two of them, right? What about over here? It's just going to be one. And it's going to be somewhere right about there. That's pretty close. It's not quite right. So here there's two, here there's only one. Now, as long as I have a continuous differentiable function, is there any way to connect these 2 points so that I don't get any tangent lines like that? So if I connect the point at A to the point at B with something that is both continuous and differentiable, meaning it's smooth, is there any way that I'm not going to have one of these parallel tangent lines?
Unless it's a straight or...
Well, okay, so let's say that we just joined it with this line. Well, every tangent line is parallel because every tangent line is that line. The only way that it could work would be if this line wasn't differentiable someplace. Like if I went up here and then went down like that, right? Now this isn't differentiable everywhere, and so I don't have a tangent line parallel to this. Okay? So this is the idea behind the mean value theorem. There are two qualifications for the intermediate value theorem, and for the extreme value theorem, we only had to have a continuous function. That was the only requirement. For the mean value theorem, we have to have a function that is continuous on the closed interval from a to b and is differentiable on the open interval from a to b, so that you can't have any jaggy bits. Then there exists a number c in the open interval from a to b such that f prime of c, that is the derivative, the slope of the tangent line, is equal to f of b minus f of a over b minus a, which is the slope of the secant line. So when they say slope of the tangent line, that's f prime of c. And this is the slope of the secant line. It's the average rate of change. Another way to say this is that at some point c, the instantaneous rate of change is equal to the average rate of change of f. Now, it's got to be both things. It's got to be continuous and differentiable. So, because if it was something like this, where I went, okay, and, oh, let's just say that, here, let's do this a different way. Let's say that I connected these two with this curve, but I went in and went, boop, that point's missing. Right? I'm not going to have a tangent line parallel to the original. So it's got to be differentiable in between. Now, do we care what happens past this? No. If it had a doink right there, does that change anything? No. So that's why it has to be differentiable on the open interval. And it has to be continuous on the closed interval because it's got to go all the way from A to B, end to end, like that. Okay? So, let's look at some example problems. Determine whether the mean value theorem applies to the given function on the given interval. If so, find the point at which the instantaneous rate of change is equal to the average rate of change. Okie dokie. So if I'm looking at f of x is equal to the absolute value of x plus 1. So I want to think about, well, what does that graph look like? That's the absolute value of x moved which direction and how far? To the left one. Okay. So we have to check both things. Is f continuous on the closed interval from -2 to 2? Is it?
Yes.
Yes. That was a long time thinking. Is f differentiable on the open interval from -2 to 2?
No.
No. It's got that sharp point, right? Where the slopes from this side don't match the slopes from the other side. So the mean value theorem does not apply. All right, let's take a look at this next one. So f of x is equal to 5 minus 4 over x. All right, well, I really don't know immediately what that looks like, but where does this one have a problem? Where is this function undefined? Yes, at x is 0, because 4 divided by 0 is undefined. But between 1 and 4, is it defined nicely everywhere? Yeah. So, are there any breaks between 1 and 4? No. So the first question, is f continuous on the closed interval from 1 to 4? The answer is yes. To see if it's differentiable or not, let's take the derivative. And remember that f of x is 5 minus 4x to the -1. So f prime is going to be what? 4x to the -2. And we can use that to answer the question, is f differentiable on the open interval from 1 to 4? Yes. So the mean value theorem does apply. So I've already got the instantaneous rate of change. That's 4 over x squared is equal to the average rate of change. So that's going to be f at 4, which will be 5 minus 4 over 4, minus f at 1, which will be 5 minus 4 over 1, over 4 minus 1. So let's see, that's going to be 4 over x squared is equal to 5 minus 1 is 4, minus 5 minus 4 is 1. Oh, hey, look at that. That's equal to 1. So multiplying both sides by x squared, I get 4 is equal to x squared, which normally would mean that x is what or what? Yeah, positive 2 or negative 2. Do both of them apply here? No. My answer must be on the open interval between 1 and 4. So my answer is only at x equals 2. And at x equals 2, since they said find the point, I'm going to go ahead and find the y value. So it's at the point 2, 3. All right, let's take a look at number 3. So first question, is f continuous on the closed interval from 0 to 5?
Yes.
Yeah, we can take the fifth root of any real number, positive or negative, right? It's with even roots that we have troubles if we want to remain within the real numbers. So that's a yes. And then f prime of x is going to be 4/5 times x minus 3 to the negative 1/5. So the question becomes, is f differentiable on the open interval from 0 to 5? Where does this function not exist?
3.
At x is 3. Smack dab near the middle of my interval, right? No. F prime at 3 does not exist. Therefore, the mean value theorem does not apply. Any questions about that? So you have to check both things. Is your function continuous on the closed interval, and is it differentiable on the open interval? All right. So let's take a look at this problem, which of course, I'm not going to be able to see all of it, but we'll get what we can. So a particle moves along the x-axis with velocity v of t, where v is a differentiable function of time t. The velocity at selected values of t is given below. So we're giving the time in seconds starting with 0 and not quite going every 2 seconds, but close to it. And then the velocity in centimeters per second. All right, so let's take a look at this. What is the fewest number of times that the velocity must be 20 centimeters per second on the interval from 0 to 12? Justify your answer. Well, first of all, velocity is always continuous, right? Until we figure out how to, transport things, teleport things into other places, velocity is continuous. And it says that velocity is differentiable. By the way, by saying that the velocity is differentiable, they're also telling us velocity is continuous, because continuous functions aren't differentiable. So, all right. So we'll start with that, because the velocity is differentiable, it is also continuous. Now, the velocity has to be equal to 20 somewhere on this interval, right? Because the velocity went from 37 to 17. And here, the velocity went from 17 to 38. So the answer is, well, twice. Because f of 0 is 37, and f of 2 is 17. So by the intermediate value theorem, f must equal 20 at some time, because 37 is greater than 20, which is greater than 17. Because 20 is in between those two, the function has to go through 20 someplace. And I didn't leave enough room for me to write in the other one. But the other one is the same idea on the interval from 10 to 12. Okay? I'm just going to put same for the interval from 10 to 12. So that's the intermediate value theorem. And then it says, explain why the acceleration of the particle must be 0 at least once on the open interval from 2 to 10. Okay, so I'm not looking at the whole interval now. I'm just looking from 2 to 10. What do you notice about the velocity at both of those ends? It's the same, which means that the average rate of change of the velocity is going to be what? 0. Okay. We need to check, does the intermediate value theorem apply here? So what are the two things we need to check? Right. So velocity is continuous and differentiable. And we can talk about the interval if you want to, but we can just say it's continuous and differentiable everywhere. So the mean value theorem, which frequently is abbreviated MVT, applies. on the closed interval from 2 to 10, the average rate of change of velocity is equal to 17 minus 17 over 10 minus 2 is 0. Therefore, by the mean value theorem, the instantaneous rate of change of the function that we're looking at, which is velocity. And what do we call the instantaneous rate of change of velocity? Well, it's the slope of the velocity. It's acceleration. The rate of change of the velocity is acceleration. Must be 0 at least once on the open interval from 2 to 10. And then it says, estimate the acceleration at t is equal to 9. Well, the acceleration is the rate of change in the velocity, right? So I can't find the instantaneous, but I can do a small interval that includes 9 to estimate it. Notice it does say estimate. For this problem, on the AP exam, they've asked questions like this, and they've tinkered around with different ones. You could do the interval from 6 to 10, because that includes 9, right? But I think that the best interval to use is the interval just from 9 to 10, because it is the smallest interval that contains 9. So the acceleration at time 9 is approximately equal to 17 minus 6 over 10 minus 9 is 11 centimeters per second per second. You get a very different approximation if you do the interval from 6 to 9 or the interval from 6 to 10. And that's okay, because they asked for an approximation. Again, I think this is the best one because it's the smallest interval that I can use that contains 9.
What if you picked like 12 to 6 or 6 to 12 or something?
Yeah, you could, in theory, pick the interval from 6 to 12 and go, well, 9's exactly in the middle of that, and that's good too. And this is part of why when they have asked this question, what they've started asking is something like, find the best approximation for the acceleration at time 7, where it's not actually in the table. And so the best one at time 7 would be the average rate of change on the interval from 6 to 9. It's a good question. This is very AP-ish, right? Where they ask things where we didn't learn the intermediate value theorem at the same time we learned the um, mean value theorem. That happens a lot where the little subparts for the stem of the problem are from completely different units. That's pretty common. Any questions? All right, so what is the maximum velocity of the particle on the closed interval from 0 to 12? This is a trick question. Figured with it being Halloween and all. It's a trick question. You have no idea. It is not possible to know from this table. Is it possible that the velocity at time 0 was 37 and then it went up to 52 and then came back down to 17? Yeah. The velocity just at those selected values, and it doesn't tell you anything more. It would have to give you more information for you to be able to figure out what the maximum velocity was.